Today we're going to start kind of a two-part lesson. We're doing day one of it, polynomial equations. We've talked about polynomials before, but we haven't done them with equations yet. So if you'll remember, equations means that things have an equal sign and you're solving. So the things that we've done before when we've done like quadratics and so forth might have been factoring, but we never had them equal to anything and then proceeded forward. That's what we're going to start with today. So the first piece on here is to talk about the zero principle of multiplication. The zero principle of multiplication says if you have two values that multiply together to give you zero, right, A and B, then either A or B was zero to begin with. I can't multiply two non-zero things and get zero. That's not possible. Okay, so it's a fact that you know, but it's a fact that you don't think of quite in that way when you're solving. So when I take a look at this problem number one, you are familiar with the idea that I take each of the parentheses, I set it equal to zero and solve. I know you're familiar with that. But the reason that that works is because of this fact. The only reason that that works is because I'm trying to figure out, well, if each of these things multiplied together gives me zero, well, one of them had to be zero to begin with. So what are the values that would make that happen? So we would set each of them 5v plus 3 equal to 0, 9 minus v equal to 0, and we'd solve. So 5v plus 3, what would I do first? Subtract from a 3. Okay, so the zeros, let me change colors here. The 3's here would cancel, and I would be left with negative 3 on the right. Then what? Divide by 5, yeah. So pay careful attention. Those are easy mistakes to make when you're subtracting or dividing, right? So this is one of my solutions. I'll write it over here. V is equal, because I'm out of space. You guys have more space vertically than mine do. V is equal to negative 5. It's not 5/3, sorry, 3/5. That's what happens when you shift around the screen. Negative 3/5. How about 9 minus V? There's a couple different things you could do. What do you want to do? Okay, how about we add the v? So, yeah, that's the easiest one to do, is to move the v. The v is already negative, so if I add the v to the other side, I won't have it negative anymore. So I have 9 on the left and I have v on the right. For those of you who were like, wait, I was going to subtract a 9, that's okay. If you had done that, you would have ended up with, we're doing v's, negative v equals negative 9, and then you would have divided by negative 1. Okay, so you still get the same answer even if you do it in a different order. So my two values that would make this whole equation equal to 0, right, satisfy my equation, are v equal negative 3/5 and v equal 9. So two answers. On number 2, you see this negative 4 out in front. So in a very real sense, we're setting each piece equal to 0, right? I mean, that's what we're really doing. But there's never a need to set negative 4 equal to 0 because it's not 0. So anytime you have a constant pulled out in front like this, you very much can ignore it because I'm looking for each piece to be equal to 0, and it isn't. It's something else. So I don't really have to do this piece. It's irrelevant to finding the answer to this question. You only need to do the other two pieces. So I need to set y plus 3 equal to 0.
Do we not have to distribute it?
And negative y minus 5 equal to 0. So we don't. And the reason we don't is because factored form allows us to set things equal to 0 and achieve the same solution. And it'll be easier to work with. So yeah, no need to distribute the negative 4 through. Our goal is going to be to put things in factored form anyway. You could also think of it like this, though, Caden. You could actually think of dividing at the beginning instead of erasing like I did kind of here. Is you could think of dividing both sides by negative 4. Like this. Because if you take 0 divided by negative 4 on the right side, you still get 0. And then these would cancel out on the left. Right? That is not a negative. Oh, yeah, it is a negative 4, sorry. So the negative 4s would cancel on the left. So you could think of it from that perspective as well. It's equivalent. Okay, we have two equations to solve. How about y plus 3? What will I do? Subtract a 3. So what will y equal? Negative 3. So this is one option. How about the negative y minus 5? Add which one? Y. Haven likes to keep his variables positive. I actually do that usually as well. So if we add the y to the other side, I have y is equal to negative 5. I said Haven. I meant Harrison. I don't know why I said that. But yeah, you're sitting right there in your cousins. So yeah, that's what it is. Okay, so we have two values. You can write them in separate boxes like I did here. You can write them inside of the single box like I did in the first problem. I don't care. But you need to show that you have two solutions. Okay?
So we really don't do anything with that negative 4?
Really don't have to do anything with the negative 4.
And that's for every problem that's set up like that?
Any problem that has a common factor in front that has no variable. Yes. So these two problems were really nice. They were really nice because they were already factored. Agreed? You already had things in parentheses, you set each piece equal to 0, and you went forward. So we're going to back it up a step now, and we're going to be looking at things that don't have stuff already factored. So when we don't have it in factored form, we have to find out what common factors we might have, and then potentially any other factoring we have to play with after that. So common factors is the first thing to look for. When factoring, consider if all terms may have a common factor, and then factor out the greatest common factor, right? The biggest thing that comes out of all the pieces. So if this one originally, number 2, had been all multiplied out, what would have been true about it is that every single term would have been divisible by negative 4. That's what it really means. So we would have been able to pull the negative 4 out in front before we actually did anything else. It would have been a common factor. So as we take a look at this, we don't look at just numbers, but it's a good place to start. So as I consider the coefficients, the numbered parts of these, what number is the biggest number that these two have in common and can be divided by? A 6, right? 6 will divide 6, and 6 will divide 12. And now you look for anything common in their variables. Do they have any variables in common? Yes, u, and exactly one u. There are 2 here, but there's only 1 here. So they have 1 u in common. So as I pull out my 6u, this is really like division. I know we've done this before. We've talked about this idea before. We are dividing 6u squared, and if I take out a 6 and a u, what's left? A u. The sign didn't change because I just took out a positive 6, so I've got a negative sign in between still. And if I have 12u and I take out 6u, right, divide, I'm dividing, what's left? 2. Okay, factoring out in front is the same as division. I am dividing it and I'm writing the value I divided by in front. So 12u divided by 6u leaves me with 2u, or really negative 2. I'm sorry, it leaves me with 2, or really negative 2 because of the sign being the same in the middle. Set equal to 0. So as we saw on the earlier screen, now I take each part and I set them equal to 0. So I have 6u equals 0, and I have u minus 2 equals 0. All right, so 6u equals 0. What would I do to solve? Yeah, I divide by 6. So u is equal to 0. u minus 2. I'll add my 2. U is just 2. And those are the two values. If you wanted to make sure you were right, what could you do? Somebody said it. Plug it back in. Thank you, Harrison. Yes. If you wanted to make sure that these values really work, that there really are solutions, just like you did back in section 2.1, you could take each of them and you could put them back into the original equation, the one before we did any factoring or anything, and you could make sure that when I put them in for you, it really equals 0 when I'm done. You can always check these problems, and these will work because we did it correctly. And if you find that it doesn't work, double check. Did you do it correctly, or did you make a mathematical error when you plugged it back in? One of the two happened. Has to make it equal, in this case, to 0. Number 4 looks like number 3, but what? What's different about it besides the specific numbers?
It equals.
Yeah, it's got two quantities, the equal signs in between, right? Everybody good with that so far? I mean, you see that that's the difference. Okay, the only way we can start with this is to move it onto the same side so that it equals 0. It has to say equals 0. Notice, this is not, the 5 principle of multiplication. It can't equal 5. It's not the x principle of multiplication. It can't equal x. It has to equal 0, and if it doesn't equal 0, everything else falls apart. So you cannot proceed unless it's already set equal to 0. So the first thing we need to do is we need to move them onto the same side, and I'm going to move my 19y. So y squared minus 19y equals 0. Always the first step is to make sure it equals 0. Now we're back to the same place we were on problem 3. I look for common factors. What do y squared and negative 19y have in common? Y. So I'm going to pull a y out. Y squared, and I pull out a y, and I still have a y. 19y, and I pulled out a y, I have negative 19, right? It's division. So I've divided by that y, it's no longer there. There's still negative 19. It's not subtraction. It did not become 18y. It's division. When I pull this number out in front, I am dividing every single time. And it's equal to 0. Then we'll set each piece equal to 0. So I have y equals 0. And I have y minus 19 equals 0. When we're looking at common factors, that's what we're doing here. It's a lot like looking at fractions and trying to simplify them and divide out their biggest common factor that will divide them both. Do you see that? I ask, what do they have in common? And I divide them by it. I'm doing the same thing here. I ask, what do they have in common? And I divide them by it, but what I've divided by is simply right in the front. So the first one's already solved. That was nice. On the second one, what do I need to do? We'll add 19. And y will, in fact, then equal 19 as my second solution. Now, the title of this section says Polynomial Equations, specifically. So what I'd like to do next is to kind of talk about more generally what polynomials are. So everything we've done so far on this presentation, the first 4 problems, all of them were polynomials. But I didn't justify that yet for you. So what we're going to do first is I'm going to give you some examples of polynomials and some things that are not examples. Okay, so a lot of times it's easier to put things into categories if you have some kind of an idea of what goes in the category. So an example of a polynomial would be 1/2 x squared plus 2. A non-example would be x to the negative 3. An example would be 3x cubed minus 7. A non-example would be the square root of x plus 2. An example would be 6x to the 4th plus 2x minus 1. A non-example would be 1 over x squared plus 7. So I've got a collection of things that work, and I have a collection of things that do not. What do you notice is in common to everything in the collection of things that work? What do you see that they have? They have exponents, okay? Can you tell specifically what kinds of exponents that they have? They're positive. That's important. What else? I'll add one to the non-examples category. What can you tell me about my exponents besides being positive? They're whole numbers. No fractions, no decimals in the exponents. Okay, that's good. What else maybe do you not see? You don't see any radicals, right? The reason you don't see radicals is because radicals are equivalent to having fractional exponents. So when I write down, whether you're remembering it or not, I'll write x to the 1/2. This is the same thing as square root of x. That's why you don't see radicals. It's because radicals are the same thing as having fractional exponents. So no radicals in my list. What do you notice is different about this one and this one? How are they different? Say it louder, Zion.
The variable and the exponent is in the fraction.
Okay, so let me adjust a little bit of what you've said. It does have to do with the variable, but specifically the variable in the second one's in the denominator of the fraction, right? Yeah. So no variables in denominators in polynomials. Okay, so there's no denominators that have variables in them. I could have fractions like the 1/2. I just don't have the fraction having a denominator that's a variable. So these are the kinds of things that we're looking for specifically. In general, this looks like a funny way of expressing this, but this is a generalized form. All of these A's with these subscripts are just numbers. And they can be any kind of numbers you want. They can be whole numbers, 5. They can be negatives, -7. They can be really, really big, 432. Or they can be decimals and be very small, 0.7. Okay? Positives, negatives, decimals, they can be radicals. The numbers themselves, the A's, could be radicals, square root of 3. They could be like pi. They could have a pi in them. It wouldn't hurt anything. So the A's really don't have anything going on with them that is outside of just any number you want. Any of those A's are any number you want. The restriction comes in on the exponents. So you guys were noticing that there were exponents in the examples that I gave, right? Yeah. And we talked specifically about what kinds of exponents we have to have. They have to be whole numbers. Whole numbers actually means positive and no fractions or decimals. So we get it all in one word, whole. So we get any whole number is an exponent. And so what you see here are just decreasing exponents, right? So this is an exponent, this is one less than this, and then down here you get 2, 1, and you have constants included as well.
Can you just write that down?
Yes, that would be a good idea. I don't know how useful it is the way that it's written, but if it helps you to see it, you're welcome to actually put some numbers in there, right? So if you want to put in some numbers, let me use black. So if you had 5x to the 7th plus 3.2x to the 4th plus, I'll use descending order, we'll do 6th, plus, so let's do minus 3x to the 5th, plus,
Are you just going to show that it decreases in the exponents?
yeah, so the standard order is to put them in decreasing order of exponents. That's what it's showing by the notation. 4/3, x to the 4th. And it continues all the way till you get to the constants at the end, if there are any. They don't have to be, but with the end we maybe have plus pi. You know, yours aren't going to be ugly like that, but they are still, I mean, this is really still a polynomial, even if it's ugly. It still classifies as a polynomial. There is a specific type of polynomial that you guys have seen, and you have seen quite frequently. And that type of polynomial is called a quadratic. So a quadratic is specifically an x squared type of polynomial. So the general form of a quadratic that we see is ax squared plus bx plus c. A, b, and c, just like my a's with the little subscripts before, can be any whole number, any rational number, any irrational number. It can be any number you want. Now, for the most part, we're going to be working with, positive and negative whole numbers and integers. That's what we see mostly. But the other things aren't excluded. And there's a few definitional things on this following. So the first one is leading coefficient. The leading coefficient is simply the coefficient, right, the number in front of the term that has the biggest degree. And that's true for all polynomials. So over here, the leading coefficient that I wrote on the example at the bottom was 5. It's got the biggest exponent, so that's the leading coefficient. Here, written out sort of arbitrarily, the leading exponent, or the leading coefficient, the largest exponent, is an A. And A is a number, we just don't know what it is, the way that it's generally speaking written here. And then these three are all talking about how many terms you have. That's why they're grouped together, they should have at the same time. A monomial means you have a single term, right? Like you've heard before of a monotheistic religion, right? Belief in one God. Mono, right? One. That's the word that's showing up here as well, mono. So for example, you could have it 3x. There's no pluses or minuses, right? It's just one term. It can have variables and it can have numbers, but there's no addition or subtraction going on. You could have something like a simple number, 5. 5 is a monomial. It's not a very exciting one. You can't do a whole lot with it. It's just a single number. But by definition, it's a monomial. It's a single term. Binomials. Binomials are two terms, like bicycle, 2 wheels, right? Bi. So if we have a binomial, it means we have 2 terms added. So maybe we have something like x plus 7. Or maybe we have something like x squared minus 2x. 2 monomial terms with subtraction or addition between. So a trinomial must mean that it has 3 terms, right? Like a triangle, 3 sides. So for this one, we have things that are 3 separate pieces separated with addition or subtraction. So something like x squared plus 3x plus 2 would be a trinomial. Or maybe you have x to the 5th minus 4x squared plus 7. That's a trinomial. 3 separate pieces all attached with addition or subtraction. All right, so correct me if I'm wrong. Have we talked about the AC method yet? Nope. Okay, different class. So this is our first exposure. I'm going to show you a couple of different ways of factoring. Okay? I don't care what way you use. It doesn't matter to me in the slightest. And there's another way that I'm not going to show you. The reason I'm not going to show it is because it causes, I don't want to say it causes more harm than good. That's not really true or fair. But it can cause a lot more confusion than helpfulness in its description anyway. So I'm just not going to show you how to do that one. The method I'm not going to show you is called slide and divide. So if you're thinking slide and divide, I love that. If you can do it and you can do it efficiently, that's fine. But I'm not going to show you how to do that method. 2 methods I'm going to show you. The first one's called the AC method. And then in the second one, we're going to use a method called trial and error. Trial and error is the only thing that was ever taught to me in school. If you like puzzles and things like that, trial and error is great. It's just like something like a Sudoku puzzle. Yay, it's a mind bender, whatever. But sometimes it can lead to very frustrating situations where you can't figure it out. So I'd like to show you first the AC method. And the reason I'd like to show it to you is because it always works. And there's a rigid format. Like you do it the same way every single time and it all pans out and works for you. These are not the kinds of problems that need the AC method as much. So if it feels like we're doing a lot of work for not a lot of gain, just bear with me. Go ahead and write it down. When we get into section, I think it's 2.3, you'll see where the AC method becomes a lot more valuable, okay? So I'm showing it to you in a very simplified types of examples. The reason I would consider these simplified types of examples is because notice what the leading coefficient is on both of these terms, or both of these problems. What is my leading coefficient?
Squared.
Okay, it's the x squared term or the variable squared term. Leading coefficient means the number in front of them. 1. You guys see that the leading coefficient on both of these examples is the number 1? Okay, when the leading coefficient is the number 1, trial and error is not usually very difficult. Okay? So when we get to trial and error and you're like, oh, that was way easier, I agree with you. I recognize that. But when we don't have the coefficient of 1, and we won't always, trial and error becomes a lot more difficult. And I mean like fast. So we're going to work with it in a simplified case first, the AC method. Okay, so the AC method, this A and this C are actually coming from, sorry about that, are coming from the expression right here. So A is the coefficient in front of x squared, and the C is the coefficient at the end. Okay, that's what the A and C are referring to. So as we're looking at this, my A in both of these cases, these examples are 1. What is my C in number 5? 10. So the AC method has me multiply these together, so that's just going to be 10. I'll write 1 times 10 as a reminder since we'll see it later. So I don't really have very exciting things show up because it didn't change C. It's the same thing C was before. All right, so that's why this is sort of like, it's an overkill approach. I recognize that. All right, so AC is 10. And then I want us to identify what the B value is. So the B value is the one that's sandwiched in between, and what's my B value here? It's -7. Okay, so here's what I'm looking for. I'm looking for two numbers that multiply to 10 and add to -7. What two numbers do that?
Wait, what?
Two numbers that multiply to 10 and add to -7. -5 and -2. Okay, so -5 and -2 multiply to 10, excuse me, and they add to -7. That's what I'm looking for. Every time I'm looking for the numbers here, I'm going to be looking for the numbers that multiply to AC and add to B. Okay, everybody good so far? Okay, so here's what we're going to do then. We're going to take this number in the middle, -7u, and we're going to break it apart. We're going to break it apart using the numbers -5 and -2. So I'm going to take these two numbers, or I'm going to take that u squared, excuse me, first and rewrite it. And I'm going to use these numbers instead with the u attached. It doesn't matter what order. You can write -5u, -2u, or you can write -2u, -5u. It doesn't make any difference. And then I have my plus 10 at the end. So what I did is I took my original trinomial and I expanded it and I made it 4 terms. Okay, is everybody good so far? All right, it didn't change anything. I just changed how it looks a little bit. Okay, why? Well, I did so because what I'm going to do next is I'm going to group things like this. First 2 terms together, the last 2 terms together. Okay? All right, so if I group these two together, I have u squared and -5u. I'm going to do the same thing I did over here when I found greatest common factors. Okay? I'm going to look at and say, well, what do they have as the biggest thing in common? So u squared and -5u have u. So we're going to pull the u out. And when I pull the u out, I'm left with u minus 5. Okay, everybody good with that part? Pulled out a u, I'm left with u minus 5. Now we're going to do the same thing with the -2u plus 10. What do they have in common? 2. So I'm going to pull out a 2. But if I pull out just a 2, I'll be left with -u plus 5. Agreed? But it'll be plus 5. Because I pulled the 2 out of the 10. So I have a 5. Yeah. But what I really want is I really want these things that are in parentheses to be the same. So instead of pulling out a 2, I could pull out a -2. Yes, I could. Now the signs change. -2u divided by -2 is u. 10 divided by -2 is -5. And these will match. If you are doing the AC method right, they always match in the parentheses. Always. Okay? If they don't, then you've chosen something that didn't work when you did your choosing of the -5 and the -2 up here. Okay, now notice the parts that are highlighted in yellow are now the same And they are common pieces to the first and into the second. They are in common, right? So what do we do with common factors? We pull them out. So now I can pull out what they have in common. They have u minus 5 in common. And when I pull out the u minus 5, here I'm left with u. Whoops, sorry, that was supposed to be a parenthesis. And when I pull out the u minus 5 here, I'm left with minus 2. Because remember, pulling things out is equivalent to dividing. I'm moving them to the front. I'm dividing by them. All I have left with the first one is u. All I have left with the second one's negative 2. And now I have it in factored form, and I'm able to complete the process like we did before. I set each part equal to 0, so u minus 5 equals 0. U minus 2 equals 0. I'll add my 5. So u is equal to 5. And I'll add my 2. So u is equal to 2. And we could check it, right? We could take 5, we could take 2, we could put them back into the original equation, and we could verify that they equal 0. Okay, let me do the AC method with you one more time. We have w squared plus 10w plus 25. So first of all, a is 1 again. C is 25. And if I take a times c, 1 times 25 is going to give me 25. Later on, we won't have a as 1. We'll have a as 2 or negative 7 or something. And the a times c will be different than just simply c. The b value is 10. So I need two numbers that multiply to 25 and add to 10. 5 and 5, right? Yeah. So 5 times 5 is 25. 5 plus 5 is 10. The numbers that I want are 5 and 5. So what I do is I take this equation and I rewrite the 10w in the middle as 5w plus 5w, and then I have my 25, excuse me, at the end. All right, so once we get it into having 4 terms, it'll always have 4 terms when we break it apart like that. We group them in pairs, and the pairs will always be exactly where they're sitting. You don't need to worry about where the numbers show up. You put the middle 2 in the middle in either order, and it will always work. This one, they're the same, so it doesn't even matter, but it will always work in whichever order. Looking at w squared plus 5w, what do they have in common? A w. So if I take a w out of w squared plus 5w, I'm left with w squared divided by w is w, and the 5w would give me 5. So far, so good? Right. The second set of parentheses. What can I take out of 5w and 25? 5. And a positive works just fine. Everything's positive on this problem. I don't need any negatives at all like I did the last one. And I have 5w divided by 5 is w. 25 divided by 5 is 5. And thankfully, these match. That's how we know we're on the right track. They have to match at this point. If they don't, you've made a mistake. Now that the pieces highlighted in yellow match, we can pull them out. All right, they're factors. This factor of w plus 5 gets moved out, and I'm left with the w here and the plus 5 here. So this piece moves here, this piece moves here, equal to 0. Sometimes the sets in parentheses do match. That's fine. It's not a problem. But it doesn't mean that it does mean that I'm not going to get 2 answers, at least distinctly different answers. Because if I set each of these equal to 0, they will be identical. So when I subtract my 5 and I get w equals negative 5, both of them do that. So So if you notice that they're the same, you don't really need to set them both equal to 0 and solve. It's perfectly recognizable at that point that there's only one solution. Okay, that's the AC method. It doesn't matter to me if you use it. If you absolutely look at this and say that's the dumbest thing that she could have taught me today, I'm cool with that. Okay? It's definitely overkill for these problems in general, but it will become useful to us next Thursday. So let me show you another method that does work really well for these problems, and that method is called trial and error. So with trial and error, tends to work very nicely when the numbers are small, first of all. I mean, I do have to have small numbers for it to be really nice, but in particular when I have a coefficient of 1 at the beginning. That leading coefficient of 1 is immensely helpful when I'm doing the trial and error method. So what trial and error method does is it immediately jumps to the factoring step. Wham, bam, you're there. There's no in between, there's no figuring things out. What happens at the beginning is that you put the two values that have to multiply to give you u squared. Well, it has to be u and u, right? That's what gives me u squared. And that's why when I have a coefficient of 1, it's really nice. If the coefficient had been 6u squared at the beginning, well, maybe I use 6u and u. Or maybe I use u and 6u, like I switched the order. Or maybe I use 2u and 3u, or maybe I use 3u and 2u and switch the order. There's lots of options, right? The trial and error possibilities are immensely more when that coefficient at the front is not a 1. But when it's a 1, there's no choice. It has to be u and u. The next thing is that I need to make sure that my sign at the end ends up being proper, right? It has to be correct. It has to be a positive. Well, the only way I'm going to get a positive at the end is if I multiply two positive numbers, right? Positive times a positive is equal to a positive. Or if I multiply a negative times a negative, that's also equal to a positive. Agreed? So when I have a positive at the end, like I've got highlighted in yellow here, what that means is the signs match. Maybe they're positive, maybe they're negative, but they match. They match, and they have to match what's in the middle. So my signs are going to be negative. Two negatives added together give me a negative. Two negatives multiplied give me a positive. This is why we worked a little bit at the beginning of this semester on thinking about positives and negatives and how they multiply together or add together to give us other values. It's because it becomes important right here. Now I think, much like I did with the AC method, I need two numbers that will give me a 10 when I multiply and give me a 7 when I add. And those numbers, as we discovered before, were 5 and 2. And if we check them, they should work, right? Negative 5 times negative 2 is the positive 10 at the end. If I look in the middle, that's negative 5u. If I look at the end, I have negative 2u. Those should add to negative 7u if we've done it correctly. You don't have to write it down, but you need to visually check it to make sure that you've chosen the right numbers. These are correct. So at this point, we are able to set things equal to 0 and solve. So u minus 5 equals 0. U minus 2 equals 0. Okay, so we add a 5. So u is equal to 5. We add a 2. And u is equal to 2. So just like before, same solutions, but a very different perspective.
On our homework, will it be like solve using the AC method?
It won't tell you. You can choose which one you want. Totally your choice. I like to show multiple ways because just because you like one doesn't mean that that's going to sort of resonate with someone else, and I want people to have choices. And if you want to use slide and divide, I know a lot of you groaned, but maybe some of you inwardly were thinking, yeah, I want to do that one. You can do that too. It's okay. I'm just not going to teach it. All right. The other one, okay, w squared plus 10w plus 25. I start out by setting up my parentheses equal to 0, right? That's the trial and error method. It just starts out with parentheses. Again, I have that coefficient of 1 at the beginning. So what will I have to multiply together to get w squared? W and w. So the beginning is easy. This one's actually really easy because all the signs are positive, right? Well, that means my signs here have to be positive too. Two positives give me a positive 25 at the end. Two positives added together give me a positive 10 in the middle. And then once again, like I did with the AC method, I need two numbers that multiply to 25 and add to 10. And those are, of course, 5 and 5. So we have each value set equal to 0. They are the same, so if you want to stop writing one of them, you most certainly can. And my W is equal to negative 5. Okay, we're almost done. Bear with me, we're getting close. I know. I'm like, oh, all right. We're going to rewind. So what we're doing next is that we're going to take our process that we just did and we're going to go in reverse. So what we just did is we were given an equation, and through some factoring along the way, we found solutions at the end. U equals 5, U equals 2. W equals 5, W equals 5. Whatever we found answers at the end, right? We're going to start with the solutions at the end, and we're going to work our way back up to find an equation. Okay, so we're just going in reverse. So here is an example, number 9. It uses the phrase roots. The word roots is the same as the word, or means the same thing as the word solution. So a root is a solution, right? The root of the problem, the solution, right? To get down to the end of it or the beginning of it. Our roots are the end of our problem. They're the solution to our problem. So we're talking about a solution, and it tells us our solutions are 6 and negative 3. So in a very real sense, it tells us the end of our problem says, it doesn't give me a variable, so you can pick your favorite variable. I'll just use x. X equals 6, and x equals negative 3. Those are the two answers at the end of the problem. Okay, so far so good? That's what that's telling you. This leading coefficient of 4, we'll get to that in just a second. So when it tells you that x equals 6 and x equals negative 3 are solutions, what we're going to do is we're going to set them equal to 0. So I'm going to shift the 6 and I'm going to shift to the negative 3 back on the other side with the x. Okay, well, we can do that. I'm working in reverse. This is x minus 6 equals 0. And this is adding my 3. X plus 3 equals 0. Okay, I'm working from the bottom up. Take a look. I started off with these two things equal to 0. I shifted them so that they're back on the same side with the variable. If I'm working my way up, what does it look like I would do next if I'm going up this sort of description? What does this step do? Puts them in parentheses, right? Multiplied by each other. That's where I am now. So I'm running out of space over there, so I'll move over here. But I had x minus 6 and x plus 3 in parentheses next to each other equal to 0. This is the point when the coefficient comes into play. At least it can here, so I'm going to go ahead and do it here. The leading coefficient is supposed to be a 4. So we're going to multiply everything by 4. It's the last thing we're going to multiply, though. So if you don't want to write it on this step, you don't have to. I definitely want to FOIL or distribute these out first. Okay, at some point, though, before I'm finished, I need to multiply everything by 4. So this x plus 6 and this x minus 6 and x plus 3 are going to be FOILed out. So first is x squared. I'll leave my 4 out here for the moment. Outer is positive 3x. Inner is negative 6x. And last is negative 18. Okay? You can combine the two x's in the middle. I have negative 3 and positive 6, which gives me, I think I just said it wrong. Positive 3 and negative 6 is what I meant to say. It gives me negative 3. So I have x squared minus 3x, and I had minus 18 equals 0. What's the last step that I would do, even though I don't have space for it? Yeah, I'll distribute my 4. So if I distribute my 4, I have 4x squared. I have 4 times negative 3, which will give me negative 12x. And then I got 4 times 18. What's 4 times 18? 72, thank you. That's one that I don't have in my brain all the time. 72 sounds right. Is that what it is? Cool. Yeah, you used your calculator. Good plan. Okay, 72, and then it equals 0. This right here is my solution. So let's check and make sure it finishes out the criterion it was supposed to. Does it have a leading coefficient of 4?
Yes.
Yes, it does. How can I check to make sure that its roots or its solutions are really 6 and -3? Plug them in, right? I could plug in 6 into the whole thing, and I could see if it works. I can plug in -3 into the whole thing that I've got in the box there, see if it works. If it does, I verified for myself that I've satisfied the conditions. Okay, we'll do one more, very similar. It says the roots are 5 and 2. So it means that x is equal to 5 and x is equal to 2. Then what? Yeah, we got to get them equal to 0. So I'll subtract my 5. So this is x minus 5 equals 0. And I'll subtract my 2. And I've got x minus 2 is equal to 0. Then what do I do? Parentheses. X minus 5, x minus 2 is equal to 0. And I know that's true because I've multiplied two things that are equal to 0, so of course they're still going to be equal to 0 when I multiply them. At this point, it tells me I've got a leading coefficient that I can go ahead and incorporate. My leading coefficient is a 2. I am not going to multiply by the 2 first. That is not a good strategy. You're going to mess things up often if you do. You're just going to confuse the situation. It's much easier to work with the distribution on the polynomial part before I worry with the coefficient at the beginning, or the binomials. So I have the first two, x squared, outer, negative 2x, inner, negative 5x, and the last is positive 10. I've got my 2 still at the beginning, so let me rewrite it. I can combine my x's here. Negative 2x and negative 5x would be negative 7x. And what would my last step be? Distribute. Yeah, the word is distribute, that's right. Distribute the 2. So I have 2x squared minus 14x plus 20 equals 0.
I was going to multiply the 2 and I